Yeah, welcome. So the topic we'll be discussing in this lecture is genetic algorithms. So basically this is a part of local search techniques. So we are discussing about local search techniques. So in the previous classes we have discussed about hill climbing algorithm, the different variants of hill climbing algorithm, and and then we have discussed local beam search, and and this is the last topic of local search techniques, that is genetic algorithm. Okay. So basically, this concept genetic algorithm is inspired from genetics, from the field of genetics. So here uh, we create states by combining two parents. So everything is called as a state. So say there is a so say one state is called as P1, another state is called as P2, and from these two states, say this is called as parent one, this is called as parent two. From this, we'll create a new state. So that is called as a child state. Okay, so this is the overall concept. So to have a brief introduction, how genetic algorithm works. So in the genetic algorithm, we'll have something called as initial population. So this the initial population contains some set of entries, or actually they are not called as entries, they are called as individuals. So let us say this is the initial population. Now the initial population contains these individuals. Here individuals is also called a solution. In the context of genetic algorithm, these individuals, they are called as either they are called as individuals or they are called a solution. So the population is nothing but a set of individual or a set of solution. Now from this set of individuals, we will be selecting few individuals. From the set of individuals or from the set of solutions, we'll be selecting few individuals or few solutions. So that is called as selection process, or it is called as mate selection. So that process is called as selection. So how do we select that? So we select those few individuals based on evaluation function, based on some evaluation function. So this evaluation function will decide the fitness of the individual. Based on the evaluation function, we know the fitness of the individual. So we apply evaluation function on all the individuals, individual 1, individual 2. On every individual we apply the evaluation function and we calculate the fitness. So once the evaluation function is applied on all the individuals, now we will come to know the fitness score. What is the fitness score of first individual, what is the fitness score of second individual, what is the fitness score of third individual, so on and so forth. Like that, we'll be understanding the fitness score of all the individuals. Now from this, we'll be selecting the best individuals. So so how many best individuals we select, that depends on the type of the problem. So we may identify top 10 best individuals, or top 20 best individuals, or top 30, or top 5, whatever it can be the number. Okay, so that is what is called the selection process. So from the set of population, or from the set of individuals, after applying evaluation function, we select few individuals. Once the few individuals were selected, then so after so once the few individual is selected, that is called that is called as mating pool is ready. So once the selection process is done, so that is, now we have a pool of individuals. So they will be getting into a process called as mating. So with mating, what happens, actually, so there are different genetic algorithm techniques are there, like crossover is one technique, and mutation is another technique. So once this mating pool is ready, they will they will they will get into the process of mating, which involves these techniques, which involves crossover and mutation. So crossover is one of the technique and mutation is another technique. So after getting through either crossover or mutation or both, the new offspring will be created. The new offspring will be created. And for this new offspring also, we will calculate the evaluation score. That is, we'll apply the evaluation function and we'll calculate the fitness score. And then we check whether the new individuals are better than the existing population or not. Okay. So basically we generate the new individuals and we will add it to the original population. So this is the process, and this process we will do repetitively. We won't stop. We will keep on doing this repetitively. How long you should do, in the sense, until you got individuals with good fitness score. So our objective is to identify individuals with good fitness score. Okay, but say initially we are not satisfied with the available fitness score of the individual, then we want to improve the fitness score. For that only we are doing all these things. For that only we are selecting the individuals with best fitness, and then uh, with that we create the mating pool, and then they get into the process of crossover or mutation. As a result, the new individuals were selected. So we check whether the new individuals, are we happy with the fitness score of the new individual or not. If you happy, stop the algorithm. Otherwise, keep on repeat this process. So this is the overall concept of genetic algorithm. So here is a flow chart. Probably this flow chart will clarify the thing. So initially we start with the initial population, and with the initial population itself we check whether the algorithm is converged or not. Converged means, with the initial population itself, uh, I mean there are many individuals in the initial population. For all the individuals we apply the evaluation function and we calculate the fitness score. So so there will be some individual with the highest fitness score. So are we happy with that individual or not? So do we consider that as a solution or not? So that is the question. So if you consider that as a solution or a goal state, then it means that the problem has converged. Then you can stop. Then you need not continue. But if it is not converged, if it is converged, stop. If it is not converged, then go into selection. That is, from the initial population, we select only few individuals. With that few individuals, we form the mating pool. And then they get into a process called reproduction. So reproduction is achieved through several techniques. Like one technique is called as crossover, and another technique is called as mutation. So there are also other techniques, but we'll be discussing only these two techniques, crossover and mutation. So 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 now it will get into reproduction, either by using crossover or mutation, or by both, by crossover and mutation, and the new offspring will be created, and the new offspring will be added to this original population. After creating the new population, for this new population also, we have to identify the fitness score by passing it through the evaluation function. And then again we check whether the problem has converged or not. That is, have we reached the goal state or not? If you have not reached the goal state, again continue the process. Keep on repeat this process until you find the solution. Okay. Some cases uh, uh, you may not be able to find a solution at all. That is, you may not be able to find a perfect solution. You may not be able to reach the perfect goal state. In that case, even though you might have repeated for several times, you might not be able to reach the perfect goal state. In that case, if it is somewhat close to the goal state, then you can stop. Or otherwise, for some type of algorithms, reaching the exact solution may not be possible. Now then you can just repeat this process for a fixed number of times. Like you may repeat this process for 1,000 times or 10,000 times or 1 lakh time, and then you can stop. So it all depends. Okay. So the so whether how long it should be continued until the solution is reached, or 1,000 times or 100 times, that varies with the nature of the problem. But this is the basic introduction to genetic algorithm. So genetic algorithm is also one of the AI technique. It is also one of the artificial intelligence technique. So this genetic algorithm is inspired from nature, and also it is inspired from the field of genetics. Okay. So with this introduction, let us get into the actual topic, right? So as I have already, as we have already discussed, so these are some of the common terms we'll be using in genetic algorithm. Individuals. Here, individual represents states, or it can be also called a solution. So everything we consider as a solution, but it is an imperfect solution. So they are denoted by strings over alphabet using zeros or one, or using some. So individuals are represented as strings. So this strings is a combination of ones and zeros. So this is how the individuals are represented. Or it can be some alphabets also, A, B, C, D, whatever it may be. Okay, but so it's a string. So basically, this string is otherwise called as chromosome, because in genetics we use the term chromosome, right? And populations are set of individuals. What is a population? Population is a set of individual or solution. Individuals are otherwise called a solution. Fitness function is an evaluation function for rating each individual. So there will be an evaluation function. This evaluation function can also be called as fitness function, which is used to rate every individual. So after applying the evaluation function on any individual, we get something called as fitness score. So that says like how much fit that individual is. Okay. And these are some of the operation. Reproduction. So a new individual is born by combining two parents. That is generally that is called as reproduction. We have two types of new reproduction. One is called as crossover. So crossover is where two parents will be joined to create an offspring. There is another style of reproduction which is, so this is actually not exact reproduction. This is one of the operation in genetic algorithm, mutation. So mutation means a new individual is slightly modified. That is called as mutation. Okay. Actually, we cannot consider mutation as a reproduction technique. Crossover is a reproduction technique, but mutation is some modification to the existing chromosome. That is called as mutation. In genetics also, mutation, what is mutation in the sense, with respect to general genetics, the, the chromosome of an individual may get affected. The chromosome of an individual may get affected either positively or negatively because of environmental effect, or because of climate, or because of the conditions in which the individual is going through. Because of that, there can be some change in the chromosome. That is called as mutation. Okay. So the point is, assume that there is a so assume that there is a parent one and parent two. So there is a child one. So that doesn't mean that the child will have all the characteristics only either from parent one or parent two. No, that is not the case. Most of its characteristics will be from parent one and from parent two. So say this is the child chromosome. Let us assume it's the child one got 45 percentage of its characteristics from parent one. Say 45 percentage. Okay, and another 48 percentage of characteristics, say let it got from parent two. Okay, so from parent two it got 48 percentage of characteristics, and from parent one it got 45 percentage of characteristics. But there is a remaining 2 percentage. This characteristics it might have received either from the nature, that is from the environment. If this individual, so I'm talking about general genetics. So if this individual, say if he is living in a very hot environment or very cold environment, or so depending on the type of environment or depending on the people to which he is exposed, based on that this 2 percentage chromosome might get modified. Originally this 2 percentage also, it might have come from the one of the parent, but due to some reason this chromosome, this small part of this chromosome may get modified. So that is called as mutation. Okay, so the mutation can happen due to environmental reason, or due to any other psychological or physical reasons. Okay. So similarly here also in genetic algorithm also we perform mutation. So mutation means from a chromosome we randomly change some bits. That is called as mutation, right? So we'll discuss all these things with an example. Probably then things will be clear. So as of now, you can understand that these are the two operations which we are going to discuss on genetic algorithm. One is reproduction and the other one is mutation. So here reproduction, in the sense we are talking about crossover. So whenever we say reproduction, actually we are talking about crossover, and another operation that we can do is mutation, right? See, here is an example on 8 queens problem, like how the genetic algorithm can be applied, or exactly this is an example for crossover. This is an example for crossover on 8 queen problem. So this is one board position. So let us call this as board position 1, and this is another board position. Let us call this as board position 2. So here the 8 queens are placed in some locations, and here the 8 queens are placed in different locations. So we can also say that this is parent 1 and this is parent 2. Okay, so this is parent 1 and this is parent 2. And this point now, this line is there. No, this is the crossover point. This line is nothing but the crossover point. So we are discussing the technique crossover. So this line is called as crossover point. Similarly, here also this line is called as crossover point. Okay, so this is a crossover point. Now we are going to apply crossover using these two parents P1 and P2. So using this, we are going to perform crossover with these two parents P1 and P2. With this, we are going to create an offspring or a child CH1. So how this crossover works in the sense, so first we have to fix the crossover point. Here this is the crossover point, right? So the child receives the this portion from parent 2. You can see the child has received the left to the crossover point, whatever the cells which are to the left of the crossover point, it has just received from parent 2. Okay, it has just received from parent 2, and whatever the things to the right of the crossover point, mm, sorry it's the reverse way. So the child has whatever the things to the left of the crossover point, whatever the things to the left of the crossover point, the child has received from parent 1. So these things were received from parent 1. You can see this queen is here and this queen is also here, and this queen is here, this is here, this is here, this is here, right? But here it is of different order. So the left side of the crossover point is received from parent 1, but the right side of the crossover point is received from parent 2. So these positions are same as this position. Okay, so this is one type of crossover. Similarly, we can also create, so there is no hard and fast rule that the left side should always come from parent 2 and the right side should come from parent 1. No, it can be other way also. So for example, the left side can come from parent 2 and the right side can come from parent 1. That may also happen. So this is just one example where the child is where the child or the offspring is created uh, by uh, by having the left part of the crossover point from parent 1 and by having the right part of the crossover point from parent 2. Okay, so this is one example for crossover. So how it is connected with 8 queen problem? So this helps us to move from one state to another state. So given these two states, now we can generate this new state, right? So then we can check the, now we can check the evaluation function for this. I mean, how many conflicts are here, how many attacks are here, how many attacks are here, how many attacks are here, then we can, that is the evaluation function. So with that, by applying that evaluation function, we can understand whether this offspring is better than the parent or not. So that's the whole concept. So like that, you keep on create offspring until until in our case our evaluation function should return the value 0, which means there is no attack at all, right? So here are some more examples. So you just recall the working mechanism of what you call the genetic algorithm, what we have discussed. So this is, there will be a, there will be initial population. From the initial population, we check whether the problem is converged or not. Otherwise we go for selection. We select the best individuals, and on that best individual we perform crossover or mutation, and then the new individuals will be produced, and the new individual will be added to the original population, and again we check whether the problem is converged or not. If it is converged, stop, otherwise continue this process. So this process will be continued until the algorithm get converged. So here is one example for that, whatever we have discussed so far in that context. So let us assume our initial population contains only 4 individuals. So just these are the 4 individuals. This is individual 1, individual 2, individual 3, and individual 4. Or you can also call this a solution 1, solution 2, solution 3, and solution 4. Or you can call it as chromosome 1, chromosome 2, 3, and 4, whatever it may be, right? Now we have applied some evaluation function or some fitness function, and we have calculated the fitness of individual 1. The fitness of individual 1 is calculated as 24, and the fitness of individual 2 is calculated as 23. What evaluation function we are using, we are not bothered about that. We are not getting into that. Some evaluation function is used, and this is the fitness score identified. And this is the fitness score of individual 3, and this is the fitness score of individual 4. Now this is nothing but the percentage, like percentage of fitness score, because if you add all these fitness score, the fitness score of first individual is 24, second individual is 23, third is 20, fourth is 11. If you add all these things, you get 78, right? So what is the percentage of fitness score of the first individual? That is how much times the first individual will be selected. So that is nothing but 24 by 78. So 24 by 78, that is 30.7. So which is close to 31 percentage. So that you got this 31 percentage. Similarly, that is calculated for all the individuals based on their fitness score, right? So this is the first step. This is so this is the initial population. All these are initial population, and this is the result of the fitness function, that is the fitness score. After applying the fitness function on the individuals, what we should go for? We should go for selection. We should select the best individuals for reproduction. So now we have our original population contains only 4. From this 4, we have to select some best individuals. How many best individuals we want to select? Again, that varies with problem to problem. So here we are selecting 3 best individuals. Our total population size is 4, but we are going to select only 3 individuals. So 3 individuals we are going to select means we have to reject 1. So who we are going to reject? The one with the least fitness score is we are going to reject. So this is the one with the least fitness score. So this individual is rejected. So remaining 3 were selected. Okay. So individual 1 is selected, and individual 2 is selected, individual 3 is selected, right? Their order can be changed, nothing wrong in that. Okay, there. So here it is of different order, and one individual is appearing 2 times. Which individual is applying? So this individual 2 is appearing 2 times. Okay, in step C in selection, you can see individual 2 is appearing 2 times because we are rejecting the individual 4. So in that position also somebody should come. So individual 2 is appearing 2 times, and individual 1 is appearing here, individual 3 is appearing here. Okay, right? Now we are going to perform crossover. Now we are going to perform crossover between what and what? So that is the question. So we are going to perform crossover. Okay, so see these 2 individuals. So these are the individuals we have selected, right? So this we are considering as parent 1, and this we are considering as parent 2. Considering this as parent 1 and this as parent 2, we are performing this crossover. So this is actually called a single point crossover. So this crossover, whatever we are discussing here, this is otherwise called as single point crossover technique. Okay, so this is called a single point crossover technique. So with this single point crossover technique, basically we can create 2 child. It's not 1 child, you can create 2 child. So this is the first child created using this crossover technique, and this is the second child created. So first child, how it is created? So this is the crossover point. This line is the crossover point for these 2 parents. So the left side of the crossover point, it comes from the parent 1, okay, for the first child, right? And the right part of the child 1, it comes from parent 2. So this is for child 1. Whereas for child 2, this is child 2. The left part comes from parent 2. Whereas for child 2, the left part comes from parent 2 and the right part comes from parent 1. Okay. So this is how single point crossover is done. Similarly, this is another two individuals, and here this is the crossover point. So here also we got two childs, child 1 and child 2. Now for the child 1, the left part comes from the parent 1. The left part of the crossover point comes from the parent 1. And the right part of the crossover point, this 1 to 4, it comes from parent 2. This part is from parent 1, this part is from parent 2. Whereas if you see child 2, for child 2, the left part comes from parent 2 and the right part comes from parent 1. So like this, we created the child after applying the crossover. Okay, so this is fourth step, crossover was done. Now we are going to do mutation. So you recall the definition of mutation. What is mutation? Mutation is nothing but randomly we change some bits. So that also happen in the normal genetics. So normally the child gets the features from the parent, but apart from that, some environmental parameters also can modify the chromosome or the gene to certain extent, to a limited extent. So that process we are simulating here. So with the mutation, you randomly select a bit and change that bit. So this bit is randomly selected for the first child and it is converted from 5 to 1. And for this second solution, we are not doing any mutation. So mutation is, it's not mandatory, right? Some cases mutation may not happen in nature also. For the third solution, we select this particular bit, this particular value, and that is mutated. Previously it is 7, it is mutated to 2. And for this solution, the last value, previously it is 1, that is mutated to 7. Okay. So this is what the final result. Now, so this is not a final result. This is the result of the one round. Now again, you have to check the fitness score of all these things. What is the fitness score of this? 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 And you have to check whether the problem has converged or not. If it is not converged, if it is converged, stop. If it is not converged, add this solution to the initial solution set or initial population, and again continue the process, and again continue the algorithm step by step until the algorithm get converged. Right. So this is the whole concept, right? This is the whole concept of a genetic algorithm. So this is, so now there are many different crossover techniques that let us try to understand the various crossover techniques uh, which is pending, right? So this is the algorithm. So it's a genetic algorithm. It takes population, the set of individuals in the initial population, and also it takes the fitness score of the individuals, and it returns an individual, uh, and it returns an individual with good fitness score, right? So input is the population or set of individuals and the fitness function, and it repeatedly does this. It repeatedly performs this task. What it does, initially the new population is set as null set or empty set. Then we are doing the loop. So we randomly select some individual as parent 1 based on the fitness score. So it's not purely random. Based on the fitness, we select one individual and we select another individual, that is parent 2, and then we, using parent 1 and parent 2, we produce the child. Okay. And after producing the child with some probability, with some small random probability, we perform mutation on the child. So that means every time we may not perform mutation we may perform, or we may not perform, based on this probability. Based on some probability, the child may get into mutation. So then, and then after mutation is done, if the probability is true, then we do mutation. Otherwise, without doing mutation, add this child to the new population. Okay. And then this new population is added to the existing population. So keep on repeating this job, keep on repeating this process until you find an individual who is fit enough. So your objective is to find an individual with some fitness score. So your objective is to find an individual with fitness score of 90%. Then until you find an individual with a 90% fitness score, repeat that. Or sometimes the algorithm may not repeat based on the fitness score. It may repeat based on time. Or you repeat this process for 2 minutes or 5 minutes or this many iteration, right? So once that many iteration is over, or once you have identified the individual with so and so fitness score, then come out and then return the best individual in the population according to the fitness function. Okay, so this is how this genetic algorithm is specified. Right? So this is the overall concept of genetic algorithm. Now let us discuss some crossover techniques. So there are different many crossover techniques. See, there is a single point. So what we have discussed there in that diagram, it's a single point crossover technique. Again, we'll be discussing that with one more example. We'll discuss all these crossover techniques maximum possible. 2-point crossover technique, multi-point, uniform crossover, half uniform crossover, shuffle crossover, and matrix crossover, and 3-parent crossover. So let us discuss the example. Let us not go into that theoretical thing. So with that example, with this example, you can understand the theoretical part. So this is an example for single point crossover. So there are two parents. There is parent one. This is parent two. First, fix the crossover point, and then this is offspring one or the child one. So for the child one, the left part comes from the first parent, and the right part of the crossover point comes from the second parent. Okay. So this crossover point is called as K, right? So if K is equal to 1, it means this is the crossover point. If here K is equal to 2, K is 2 means this is the crossover point. This is K is equal to 2, right? If K is 1, then this will be the crossover point. In this case, our K is 2, right? And in case of child 2, for child 2, the left part comes from parent 2 and the right part comes from parent 1. So this left part, it comes from parent 2, and the right part of the crossover point, it comes from parent 1. So this is how the single point crossover works. In case of 2-point crossover, so the next technique is 2-point crossover. Here we have two crossover points. So we have two crossover point. One is K1, this is K1, and this is K2. So with 2-point crossover, also we can create two childs, child 1 and child 2. So this, for child 1, see, this part is intact. For this part is coming, this part of child 1 is coming from parent 1, and this part of child 1 is also coming from parent 1, and the bits or the genes which are in between the crossover points, they are coming from parent 2. So this is from parent 1, this is also from parent 1, whereas this point is coming from parent 2. Whereas in case of child 2, this point is coming from parent 2, right? And this point is coming from parent 2, whereas this in between point is coming from parent 1. So basically the between point alone is swapped. Otherwise, the whatever the chromosome or whatever the gene which is present between the two crossover point, they were swapped. The other parts were directly inherited from parent 1 to child 1 and parent 2 to child 2, right? But there is no hard and fast rule like this. It can be also the reverse way. It can be also the reverse way. For example, we can keep this part intact and we can swap this part, right? That is, this part of parent 1 may go into child 1, and this part of parent 2 may go into child 2, and this part can be swapped for both the parent and the child. So for child 1, this part will go and this part will go, and for child 2, this part and this part will go. Are you getting? So there is no hard and fast rules that we have to follow this strictly. Instead, it can be done in the reverse way also. For example, we can also create a child 1 and child 2 like this. That is, we can keep this, we can keep this middle part intact for both child 1 and child 2. That is, child 1 will get it from parent 1 and child 2 will get it from parent 2. So in that case, child 1's the middle part, first I am writing. So child 1's middle part will be from parent 1, that is 100. But the other part it will be getting from parent 2. So this will be 10, okay, and this will be 100. Whereas for child 2, it will be getting the middle point from parent 1, it 100, 101, not 100, it is 101. So this is 101, okay. But the other part, it may so the middle part it is getting from parent 1, right? The middle part it is it is getting from uh, parent 1, parent 2, sorry, the middle part it is getting from parent 2, and the other part it may get from parent 1. So this can be 0 1 and this can be 0 1 0, right? So this is nothing but the reverse of this. So either, so keep something, either keep this as intact and swap the, either keep the middle part as intact and and swap the outside part, or keep the outside part intact and swap the middle part. So here we have kept the outside part intact, that is, child 1 is getting from parent 1, child 2 is getting from parent 2, the outside part, but the middle part is swapped, right? But it can be done in the reverse way also. So this is this style of a crossover, that is called as 2-point crossover, okay. So so next we have multi-point crossover. So in multi-point crossover, there is no restriction. You can have any number of crossover points. So here we have 3 crossover points, k1, k2, k3. Now how the offspring will be generated? So the offspring can be generated by swapping the alternate parts. So in case of multi-point crossover, a number of crossover points are selected along the length of the string at random. So you can randomly select the number of crossover points. The bits lying between alternative pairs of sites are swapped. The bits lying between alternative pairs are swapped. Okay. So 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 for example, see, this is offspring 1 and this is offspring 2. If you see offspring 1, how it is generated, for offspring 1, this first part is coming from parent 1, whereas second part, first part is from parent 1, second part is from parent 2, again third part is from parent 1, fourth part is from parent 2. So alternative things were coming from parent 2, but other things were from the parent 1. Whereas for offspring 2, the first part is coming from this part is coming from parent 2, whereas this is from parent 1, again this is from parent 2, and this is from parent 1, right? So this type of crossover is called as multi-point crossover, right? Then we have something called as uniform crossover technique. Yes, with uniform crossover technique, what we do, in the sense, here we have two parents, parent 1 and parent 2, and then based on some probability, we decide like whether the swapping will be done or not. So there's something like a coin tossing. We are tossing a coin. Say whenever there is a 1, there is a head. Whenever there is a 0, there is a tail. So let us assume that when there is a tail, whenever there is a tail, we should swap. When there is a head, you need not swap. So when there is a tail, that is when it is 0, we are going to swap. So 0 we are assuming as tail. So here this is the coin tossing. So first, for the first bit of the chromosome, it is 1. So it means no swapping. So it comes as it is. That is, parent 1 goes to child 1 and the parent 2 bit goes to child 2. So it comes as it is. But in the second case, there is a tossing. So I mean, there is a tail or it is a 0 in the coin toss. So we are swapping. So the 1 from parent 2, it comes to child 1, and the 1 from parent 1, it comes to child 2. With respect to value, in this case, there is no change with respect to value. But actually the swapping has happened because both of them has the same value. So we are unable to differentiate. So let us see here. The third case also, it is tail. So you should swap. So swap means what? Swap means the one of parent 2 should goes to child. So the child got 1 from parent 2. And the 0 of parent 1, the 1 of parent 2 should go to child 1. And the 0 of parent 1 should go to child 2. Okay. And in this case, there is no swapping. So the 0 0 comes as it is. Here also there is no swapping. So 0 0 comes as it is. Here also no, here no swapping. So this 1 1 comes as it is. Again here there is a swapping. So this 0 1 becomes 1 0. Here it is 0 1. Here it becomes 1 0. Right. Again in this case there is no swapping. No swapping. So no swapping. 1 1 comes as it is. Here 1 0 comes as it is. Here there is a swapping. So 0 1 becomes 1 0. Again here there is a swapping, but it is 0 0. So there is resultant, there is no change, it is 0 0. In this case there is no swapping. So this is how the offsprings were generated using uniform crossover technique, right? Okay, fine. So this is another technique. This is uniform crossover with mask, with crossover mask. Actually the logic is same here also. This is also very similar to the normal uniform crossover technique, but the only difference is here instead of using coin tossing, we fix a mask. So apart from parent 1 and parent 2, we have a mask. So the mask contains the values. Like already, it's not that we are going to toss a coin and whether it is head or tail. No, there is a mask. This mask contains some string. Basically, it is a collection of ones and zeros. So based on this mask, we are going to decide like whether a particular bit for the offspring will it come from which will it come from parent 1 or from parent 2, right? Based on this mask, we'll be deciding like the particular bit of the offspring will it be coming from parent 1 or from parent 2. So for offspring 1, how it is calculated means when there is a 1 in the mask, when there is a 1 in the mask, the gene is copied from parent 1, else from parent 2. Okay. So if there is a 1 in the mask bit, if there is a 1, the gene is copied from parent 1. Otherwise, it is copied from parent 2. So here there is a 1. So this is copied from parent 1, right? Here it is 0. So it is copied from parent 2. Here it is 0. So it is copied from parent 2. Here it is 1. So it is copied from parent 1. Here it is 1. So it is copied from parent 1. Here it is 1. So it is copied from parent 1. Here it is 0. So it is copied from parent 2. Here it is 1. So it is copied from parent 1. Right? Similarly, for offspring 2, it's the reverse way. When there is a 1 in the mask, the gene is copied from parent 2. When it is 1, it will be copied from parent 2. When it is 0, from parent 1. So it is 1. So it is copied from parent 2. Okay. Sorry. When there is a 1 from parent 2. When there is a 1 in the mask, the gene is copied from parent 2. Yeah, else it is from parent 1. So it is 1. So it is copied from parent 2. Here it is 0. So it is copied from parent 1. Right? Here it is 0. So it is copied from parent 1. Here it is 1. So it is copied from parent 2. Here it is 1. So it is copied from parent 2. Here it is 1. So it is copied from parent 2. Here it is 0. So it is copied from parent 1. Here it is 1. So it is copied from parent 2. Right? So this is how this uniform crossover technique with mask works. Basically, the working style is same as that of generic uniform crossover, but there it is causing tossing of coin, but here it is actually based, we fix the mask. In the mask we put some values, and based on that, that controls the crossover. Fine. So the next technique what we are going to discuss is half uniform crossover. So with half uniform crossover, what we are going to do is we are going to perform this tossing. So so we are going to perform tossing only only if the parent and the only if both the parents don't match. Only if both the parents don't match, only on that positions we'll be doing this coin tossing. So here this point you can see parent 1 and parent 2 are same. So there is no coin tossing here, right? And this point they are not same, so there is a coin toss. Again here they are same, so no coin toss. So here there is no coin toss, here there is no coin toss. Here they are different, so there will be a coin toss. Here they are different, there will be a coin toss. Here they are same, so no tossing of coin. Here they are same, no tossing of coin. Here again they are different, so there will be a coin toss, right? So whenever there is a coin toss, whenever there is a coin toss, what will happen? See, if there is no coin toss, the bits in the parent one will, the bit in the parent one will come directly to child one, and bit of the parent two will come to child two. That's it. And when there is a toss, when there is a toss, and if there is a one, if there is a one, then they will be swapped. So as a result of toss, if it is one, then they will be swapped. If it is zero, then there is no swap. If toss is one, then swap. Otherwise, the bit remains the same, right? So that is the rule of the game. So here there is no toss at all. So just the one of the parent one and two, it comes to the child one and child two as it is. Here there is a toss. The result of toss is one. So if the result is one, then swap. So this 1 0 becomes 0 1. Here there is no toss. So just 0 0 it comes. Here there is a toss, but the result of toss is 0, which means there is, you are not, again we are not going to swap. The same 0 1 comes as it is. Okay. Here it is 1, which means we should swap. So this parent 1, this 0 1, it becomes 1 0, right? Again here there is no toss, no toss at all. So the parent chromosome comes as it is, as 0 0. Again no toss, so the parent chromosomes 1 1, it comes as it is. Again here there should be a toss. There is a toss and the result is 1, so we have to swap. So this 0 1, it becomes 1 0. So this is how half uniform crossover technique works, right? And then we have something called as shuffle crossover. So what is shuffle crossover? Actually, this is very similar to that of a single point crossover, but before crossover, we are doing some shuffling. So this is before shuffling. Okay, this is before shuffling. This is after shuffling. Here we are selecting some bits to shuffle. So these two bits we are going to shuffle. So you can see here, these two were shuffled here. So this is 1 0, here it becomes 0 1, right? Similarly, these two bits were shuffled. So this one will go here and this 0 will come here. So this 0 comes here and this one came here. Similarly, this also it got shuffled. This 0 came here and this one came here, right? So this is after shuffling. Then this is the crossover point. So this is the crossover point, and here we are performing now the normal crossover, right? So for the first child, the left part it comes from the first parent, and the right part, the left part it comes from the parent one, and the right part comes from the parent two. Whereas for the second child, the left part comes from the parent two, and the right part comes from the parent one. So this is normal single point crossover. Fine. So this let us not get into this matrix crossover. Then we have three parent crossover. So with three parent crossover, how it works means, in case of three parent crossover, three parents are randomly chosen, right? Each bit of the first parent is compared with the bit of the second parent. So first, just we compare the first parent bit with the second parent bit, each bit. If they are same, then the bit is taken for the offspring. So there are three parents, P1, P2, and P3. we compare each bits of the first parent and the second parent. If they are matching, then that bit will come into the child as it is. So here we have only one child, not two child. So whatever the already it is matching. So the same bit which is matching in parent 1 and parent 2, that will come to the child as it is. Suppose if it is not matching, if they are not matching, then the bit is taken from the third parent. That's it. So it's a very simple technique. So here these are the three parents, P1, P2 and P3. Now you can see here the first bit of parent 1 and the first bit of parent 2 are not matching. So for the child, the first bit comes from the parent 3. If they don't match, it comes from parent 3. The second bit of parent 1 and parent 2 are matching. So it comes either from parent 1 or parent 2. Right? The third bit of parent 1 and parent 2 are not matching. So it comes from parent 3. The fourth bit of parent 1 and parent 2 are not matching. So it comes from parent 3. And the fifth bit of parent 1 and parent 2 are not matching. So it comes from parent 3. The sixth bit of parent 1 and parent 2 are matching. So it is coming from parent either from parent 1 or parent 2. And the seventh bit of parent 1 and parent 2 are matching. So in that case, it will come either from parent 1 or parent 2. And the last bit of parent 1 and parent 2 are matching. So it comes either from parent 1 or parent 2. Right? So whenever they match, it comes from any one of the parent, either parent 1 or parent 2. If the parent 1's respective bit and parent 2's respective bits were not matching, then it will come from parent 3. Okay. So that's it about what you call genetic algorithm, right? And that's it about the different crossover techniques. Fine. Let us stop here for today's lecture. Thank you.